Hi, I want to take a second look at the force of gravity. Up until now in class, we've been assuming that the strength of Earth's gravity is always about 9.80 meters per second squared. Now, depending on which lab you're in on main campus, we'd say use 9.8014 meters per second squared for the value in lab. But at Akron, I mentioned use 9.8017 meters per second squared. Clearly that means that strength of gravity can't be constant. But aside from the fact that I'd tell you to use two different values depending on where you are, is there other evidence that we have that this can't be the case? Well, for the case of an object that's in orbit, the force of gravity is acting as a centripetal force. It's always pointed in towards the center of an object's orbit. So if we had a constant force of gravity, the mass of our object times a constant strength in the negative radial direction, well, from Newton's second law for rotational motion, that would be minus the mass of our object times our centripetal acceleration, the speed of the object in orbit squared, divided by the radius of the orbit. And again, it would have to be in that exact same direction as the force, in towards the center of the orbit. So equating those two pieces tells us that the orbital speed should be the square root of the strength of gravity times the radius of our orbit. And since the speed of an object in orbit is going to be the circumference of the orbit, 2 pi times the radius of the orbit, divided by the period of the orbit, the time to make one trip, t, the period would be 2 pi times the radius divided by the speed, which means the period should be equal to 2 pi times the square root of the radius of the orbit divided by the strength of gravity. So, let's look at a couple of items. Say that we're looking at the International Space Station. The International Space Station's a little bit above the surface of Earth, so let's estimate that its radius of orbit is about 6.6 times 10 to the 6 meters. So, if I take that value and plug it in to find its speed, 9.8 times 6.6 times 10 to the 6 meters, the square root of that gives me a value of just over 8,000 meters per second, 8 kilometers per second. Actual speed's around 7.9 kilometers per second, so we're close-ish. The period that we'd predict, 2 pi times 6.6 times 10 to the 6 meters divided by 9.8 meters per second squared, under our square root, would give us 5,160 seconds, which is about 86 minutes, which is about 5 to 6 minutes lower than the actual time. So let's look at an extreme example. With the moon. Now, it turns out humans have known about how big the moon is, about how far away it is, and how long it takes the moon to complete one trip around Earth for pretty much 2,500 years that we have record of. So, we know in modern units the speed of the moon is 1,000 meters per second. Well, if we were to do the same calculation out at the distance of the moon, which is about 7.35 times 10 to the 8 meters, if the strength of gravity were still 9.8 meters per second squared, then the moon would have to be traveling at 85 kilometers per hour because the moon would only be taking 11 hours to orbit Earth, which clearly isn't the case. We notice the phases of the moon take around a month. That means we'd expect the time for the moon to orbit around Earth should be around a month. It's actually about 27.4 days, which is clearly more than 11 hours. And 1,000 kilometers or 1,000 meters per second isn't 85. I said kilometers per hour. I meant kilometers per second. So clearly that can't be the case because it turns out at that speed, the moon would actually be escaping from our solar system faster than anything humans have ever been able to achieve. The moon doesn't do that. Clearly something has to change, and the answer lies in how Newton was able to apply his laws of force to explain why we have an approximately constant strength of gravity. Thanks for watching.